Yeah. 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 The slides will be available. This is being recorded as well, so it'll be online. All the material will be online at Bitbucket. So yeah, it'll all be available afterwards. Yeah. All right. SDL, yeah, that's one of the dependencies of PyGame. Yeah, so you should just be able to. You're on Linux? No, yeah, Windows? Yeah. If you're on Linux, then you should just be able to apt-get install libSDL and stuff like that. Well, yeah, there's a bit of time before we actually start executing code, so yeah, I've got a bit of an introduction first, so yeah. I think I'll get started though. All right, good to go? All right. Welcome everyone, thanks for coming along. Yeah, today I'm hoping to teach you the basics of how to write a game in Python. The basic ideas are transferable to other languages. So I'll be talking about some kind of basic concepts of game programming. And hopefully we'll get through writing a game that'll demonstrate all of those kind of basic principles. So I'm just going to tell you a little bit about me. I'm going to cover some kind of initial thoughts about developing games and kind of what that involves. We're going to construct a game piece by piece during the tutorial. I'm going to show you some code to demonstrate how you might implement some different types of games beyond the one that we developed during the tutorial. I'll talk a little about packaging games, how you can package the Python application to distribute to other people to play. And I'm going to talk a little bit about content tools to actually develop the content for games. And hopefully everyone will have PyGame working by the time I get to code. Oh yeah, go Mac. Apple does like to make our lives interesting. Okay, so a little bit about me. I've been mucking around with computers for quite some time. My first computer was a Commodore 64 back in the 80s. And I played a lot of games on it, and I wrote a few games in BASIC on it, and that was a bunch of fun. And then I got an Amiga. I had a couple of different Amigas, and I played a lot of games on that too. And I was still writing games on that. And then I went to university and graduated, got a job, and I stopped writing games. I still played a lot of games, but I basically stopped writing games because I had a real job. I did dabble with the web very early on in the mid-90s, and I made a silly little game on the web back then. But we didn't really know much about web application development in the kind of the mid-90s. It was pretty horrendous, and persistence was a real problem. And so that was kind of an experiment that didn't go very far. And then nothing until I rediscovered the joy of writing games using PyGame in 2004. So PyGame is very mature by now. It was mature back then, and so it's extremely mature now. It's a very solid platform for writing games in. And in 2004, I discovered an online challenge called Ludum Dare 48, which is a challenge to write a video game in a weekend, a 48-hour game programming challenge. And I enjoyed that so much, I ended up running one of them as well. And then and I had so much fun doing that, I decided to start my own challenge, which is called PyWeek, which is about writing a game in a week. Because along the way I became a dad, and I found that weekends were a bit hard to dedicate to just writing a video game. So that's a little bit about how I got here. I also created the Cheese Shop, and I still run that. And I wrote Roundup, which is the bug tracker that Python project uses, and a few others. And I run PyWeek. So that's a little bit about me. I'm kind of all over the place, but I really like games. So before we actually get into actually writing a game, we're going to talk a little bit about what you might like to actually create. I'm just going to do a little thing here. So we're just going to spend a few minutes thinking about what games are, which will hopefully help you kind of focus on the things that are important to you during the tutorial today. And may actually prompt questions, which I love questions. Questions are good. So does anybody have in their mind a game that they'd actually like to create? Yes?
Pretty complicated, which is why I stuck.
Right.
It's complicated to get the idea down to in such a way that I can actually have the concepts of the game clear enough that I can program them.
Okay.
Been working on it.
Well, if there's anything particular that you're stuck on, or that you think you might be stuck on, then just let me know if I haven't covered it. Yeah.
So mine's a little off the wall, I guess. Mine was to create a game that would allow our internal IT department to complete rudimentary, pretty boring tasks in a fun way. So maybe they go through this game, and when they get to this requirement, they'll actually execute this task on the back end for them on the infrastructure.
So kind of like the demon killing using the Doom front end.
Yeah.
Yeah. Okay.
It would actually, interact.
Right. Cool. We know about the Doom front end to the kill command. Yeah. Okay. So one of the important concepts in defining what a game is talking about genre. Genre is a kind of a funny thing. A shoot 'em up game, that's kind of a genre of video games. It's very much the staple of video gaming. You move the little avatar around on the screen, and you shoot some other little avatars on the screen, and you try to avoid the things that will kill you. This is one of the very earliest known video games. It's called Space War, and it was a shoot 'em up. It was a two-player game using vector graphics, and it was pretty amazing at the time. This is a beat 'em up, which is kind of like a shoot 'em up, except it's got some constraints on the gameplay. It usually has some emphasis on sort of rock, paper, scissors style attack and defense combinations. And there's memory game combinations in there as well, usually for gaining extra power. The platformer, which is basically the same, but you're walking and jumping and swinging and rolling and jetpacking and whatever else around the level. Puzzle games, on the other hand, are actually quite different and more about contemplation and finding tricky solutions to problems. Having said that, a lot of games can include puzzles in them while not being strictly puzzle games. So the whole idea of genre can be quite malleable. Exploration games give a player a world to explore. They might also be given things to do in that world that can change the world, but that's not necessarily a requirement. Typically, there can be puzzles to explore, but again, those puzzles might be extraordinarily basic, just as a way to limit the player's progression through the exploration of the world as the designer sees fit. And then there's action-adventure games, which blend action with exploration and puzzles. Strategy games, which rely on the player's decision-making skills and thinking and planning. They're often about empire-level struggles against other empires, but they can also be quite abstract, like chess and Go. They can be slower and contemplative and turn-based, or they can be real-time, which blend strategy and action. Some strategy games lean strongly towards puzzles, tower defense games, are a good example of the kind of puzzle strategy game. And then we have simulation games, which focus on the mechanisms that make the world tick. So they give the player pretty direct control over the mechanisms that make the world go. And there's an emphasis on attempting to realistically model real situations. So something like SimCity, but also car driving games, basically trying to simulate a vehicle, which is a sort of a slight variant of the action genre. Role-playing games, or RPGs, which are basically exploration games most of the time, but there's an emphasis on the player's character being able to grow or be customizable through the game. Often the player can also change the world in some way as part of the ongoing exploration or story in the game. There's even subsets of RPGs, so the Japanese role-playing games, or JRPGs, which follow a fairly specific formula, and a lot of them are very much like simpler action-adventure games. But in the end, they're very much just like exploration games with a few extra bells and whistles. And then there's FPS, which some people would say is a whole genre into itself, but it's really just another way of looking at things. It's just an action game. The first first-person shooter games were actually just role-playing games, but with limited freedom compared to Doom. So this is Akableth, which was made in 1980, and it was a first-person game. Not really a shooter, but it was first-person. So in my mind, these are the basic kind of 6 genres of video game. And of course, the genre of the game that you create could blend any of them. I haven't even talked about multiplayer because it's kind of just an extra thing that you can add, but it does dramatically change most games. So these are kind of the 6 basic flavors that you can mix into to make a game up. And then on top of that, you can throw in an extra or any number of extras. These like single little mechanics that can extend the basic genres. Some of these, like New Game Plus, which basically says that once the player reaches the end of the game, they can restart the game with some modifications on the game so they can retain the power-ups that they've received during the game and play through the game again. Nintendo Hard is a reference to games like Super Mario Brothers, which are incredibly hard at times, even though they are packaged up as something that's cute and simple. One button, I guess Flappy Bird is a good example of a one-button game. And so you can mix all of these things, or just one of these things, into most of the other basic genres. And this is by no means an exhaustive list. This is just the stuff I came up with off the top of my head. Then so those are kind of patterns, and these are the anti-patterns, the things that you should avoid. These are the things that you shouldn't include in your video game. Zombie closets. I'm sure if you've played Doom or anything similar to Doom, then you'd be familiar with the concept of walking past a closet and to have a zombie come out of it. And eventually you become conditioned to know that when you're walking along a corridor and you see a closet, you should always turn around after you've passed it, because there'll be a zombie behind you. Goddamn Bats there was a famous, now I've forgotten the name of it. There's a famous video game from the 80s in which the player had a single attack, which was horizontal. It was a platform game, and they had a horizontal attack. And the game designer had included these bats that fly down from the top of the screen to attack the player. But the player can't actually attack them until they are level with the player. But usually the player's dead by the time they're level with the player. And they were called the Goddamn Bats. Artificial stupidity, referring to artificial intelligence that's particularly poorly implemented, which tends to just annoy the player because NPCs get stuck on walls or things like that. Yes. The vanishing platforms of, invisible and vanishing platforms, things that instantly kill the player with absolutely no warning. That's a bad thing. Anyway, so there's a bunch of things there that to try to avoid. And again, that's not a comprehensive list. There's a great online blog called Bad Game Designer No Cookie, which catalogues a whole bunch of this stuff. Grind. Well, the success of WoW kind of says that that's not necessarily an anti-pattern. People seem to like it, but I think that perhaps it's not such a good idea. Okay, so that's the kind of the mechanics of the game. And once you've thought about the mechanic of the game that you'd like to create, you can then start thinking about what it looks like and where it's set. And this is when I was talking about first-person perspective or first-person shooters. That's kind of part of this, which is just the way that the game is presented to the player. Whether it's a 2D game or a 3D game, whether it's first person or third person. But also the art style of the game as well, which is influenced by the setting. As a fledgling game developer, I imagine you'll probably be not very confident, or you may be confident in your art skills, but if you're like me, you're not very confident in your art skills, and that's fine, because you learn art skills as you go along. But you may be lucky and you may know an artist who is willing to jump in and help you make a game, in which case you're probably just constrained by whatever they like to draw. But again, like the genres, you can take these and mix them up, so you can have the zombie space horror, or the, I don't know, flying romance, steampunk romance, flying islands. Zombie aliens are always popular. Superhero aliens. And again, not a comprehensive list, just stuff I came up with off the top of my head. An important point to make, though, is that, so you've got all these potential ideas. It's very important that when you're starting out, you start small. You think of that one thing that you think is pretty cool, and you focus on it, and you don't add on more ideas. You start with that one thing, the simple game, one mechanic, maybe two. Try to limit it to just one mechanic. So if it's a platform game, just stick with jumping around and shooting things. And you do that. And be prepared for it to suck. Okay? Your first game, your first 2 games, 3 games, for me it was the first 3 or 4, aren't going to be very good. And that's perfectly fine. Everyone goes through that. Just start with something small. Don't get too ambitious. Save the amazing game for after you've knocked out a few simpler games. And build on it. It's very much like learning any other thing in programming. Start with something small. Okay, so having said that, how are we all going? Have we managed to get PyGame installed and running enough? Does everybody have the contents of the USB stick? There's a few of those floating around. All right, well, if you don't have PyGame up and running, then you can probably just, sit with a friend or make a new friend. But I think we'd better get going. So let's make a simple game. So to make a game, we have some basic core elements that we have to get done. We have to, and you can have games that don't have some of these things, but that's fine, but I'm going to talk about your typical game. So you need to display something on the screen. You need to handle input from a user, a player. You need to implement some gameplay mechanics that respond to the user and implement things going on in the world. You need to play sound effects and music. And then there's an overall kind of software architecture that you should be thinking about as well. How are we going?
Doesn't work.
Sorry?
PyGame doesn't work.
Doesn't work. Yeah? Okay. Okay. So I'm going to talk about all of these things during the course of constructing this simple game that we're going to work through. So displaying something on the screen, we'll need to open a window on the computer, draw something into it, and possibly move it around. And again, there are some games that can omit some of these things. So you can have games that just display pictures on the screen and don't move anything around. You can have exploration games where there's a static image displayed and you just handle clicks on that image. But we're going to talk about the whole lot. Something that's important to understand is that if you have a game that's full screen, it's still in a window. It's just that it's a full screen window. So we're always opening a window on the screen. To draw things on the screen, we can take an image that we've got stored on disk and we can just copy that straight onto the screen. We can draw individual pixels, either one at a time or in a line or in various other shapes using the PyGame.draw module. We can draw up text using the PyGame font module, and that draws nicely anti-aliased true type fonts text. Or we can skip all of that and use OpenGL, which I'm not going to cover today, but it is an option. PyGame does give you the option to open a window that will give you an OpenGL context, and then you can use something like PyOpenGL to draw 3D graphics. All right, so we can load images off of disk, PNGs, JPEGs, and a variety of other format images. We can also construct images in memory using the PyGame surf array module, which allows us to use things like NumPy to generate images mathematically, and then construct a drawable image from that. We can also draw to an off-screen surface, draw patterns or whatever to an off-screen surface using PyGame Draw and all of the other mechanisms, and then copy that up onto the screen, possibly multiple times. We're getting close to having anyone getting PyGame working? Yeah? All right. Yeah?
Binaries on Windows seem to work.
Yes, binaries on Windows do work.
Compilation on Windows doesn't work.
No.
On Linux doesn't work. It doesn't work.
Wow. Okay, so we've got a few people going. So, opening a window in PyGame, it takes a couple of commands. First of all, we need to import PyGame. And then one of the first steps in a PyGame program is to initialize PyGame using PyGame init. And then, excuse me, and then we obtain a window using the slightly obscurely named display.set mode, which PyGame actually starts with a hidden window, and set mode sets sets flags or dimensions on that window to the actual window that you wish to have. It opens the window so that there is, at pygame.init, it creates that window so that subsequent commands have a valid context to work in, even if you're not displaying a window. This can be important, especially for things like OpenGL. Yes, question?
I was going to ask if that was what the display variable was.
Well, display is a module inside PyGame. Yeah. So if you would like to run the file 01 open window, you'll see that actually work if you didn't want to type all that in. There's actually a bunch of typing. You can try and keep up, but that's fine. But if you don't want to keep up, then each one of these steps is just in a numbered file as we go along to try stuff out. So if you do run that, don't be alarmed if you don't get a window that stays up, because it's not going to stay up. Because there's no further code in our program, the program just exits and the window closes. So what we need to do is introduce something that will keep the program running. The simplest way of doing that is just to put something at the end of the file that says while true, pass, and that'll just keep the program running. It'll use a lot of CPU as well, but it'll keep things open. What we tend to have in our PyGame applications is a thing called an event loop or a main loop. And what this does is it has two basic purposes. Well, three, I guess. One is to keep the program running so that you can still see what's actually being displayed. The second is to handle events that are going on in the system, which can include basic system events like the window being closed or keyboard events. And also it can be responsible for refreshing what's being displayed on the window. Here we just have the basic event handler, which we ask for all of the events that have happened since the last time we asked for events. PyGame just keeps a queue of events in memory, and so PyGame event.get just retrieves that queue for us. And each of the events has a type. You can see I've got two different types of events here. There's the quit event, which is what the operating system will send us if the window is closed. PyGame also generates that on macOS, for example, if you use Command Q. We also handle a key down event for the escape key. There are two events for key presses, key down and key up. And I'll come back to all of that later, but there's multiple different types of events. There's also mouse movement events and mouse button events and a few others. You can also create your own event types as user events. So if you want to see that running, you can run 02 main loop and you'll get a blank window opened up. It's very exciting, but at least it's there. So now on the subject of software architecture, so that's an event loop, and pretty much every single game has one of these. Some game frameworks implement their own event loop that you kind of attach event handlers to. PyGame has a very low-level view of event loops where you implement your own. Piglet, which is another Python game development framework, you register event handlers with an existing event loop because it does a bunch of other stuff, OpenGL stuff, that it has to manage. So we're going to talk a little bit about structure. This is not a very good structure in terms of software architecture. It's just all jumbled into the top level of a Python module. So we're going to take this and we're going to introduce a very basic structure into it by creating a class which has a single method, main, and then inside our module we'll execute that main if the module is invoked as a program. So now we have, instead of having just some top-level script that can just be run, we have some code that's standalone, it's re-enterable, it can store its own state on its own object. On the game object, we can store state for that game. We can create the game multiple times, so if we need to restart the game, we can just ditch the existing game object and create a new one. We can store references to the player, the playing field or the level. We can have enemies, we can have bullets, all these things stored away on the game object, nice and neat. We can pass that game object around to things if they need to access the state of the game. No global variables, which is, that's a goal in software architecture as a general thing, no global variables. This game object could also just be called level or world or something like that, but I'm just going to call it game. If you wanted to have multiple different types of levels in your game, you could have multiple game classes or level classes, and each one has its own event handler. As long as you have some way of getting out of that while loop, so for example, you can hit the escape key to get out of this one, you can then go on to launch another one. So if you want to have different scenes in your game or different levels in your game where they all have their own event loop and their own implementation, you just have to have a way of getting out of that while loop and launching a new one. Or inside that event loop, you can jump off into some other level's event loop, and it starts consuming the events from PyGame. So that's a nice, neat way of doing the basic structure of a game. Okay, so enough boring software architecture. Let's talk about drawing. So here we have programmer art. This is what we're going to use as our image to draw on the screen. Once we've achieved drawing stuff on the screen, there's a whole stack of games you can implement. There's adventure games, there's Tetris, Minesweeper, stacks of games. Okay, so this is the core and basic thing that you need to be able to get done. And seriously, when you're starting out, just draw stuff like this. It's good enough. It tells you what the thing is. You can polish it up later. Or when you realize the game is not very good, throw it away, move on to the next game. If the game is fun, it doesn't really matter what it looks like. So what we want to try and do is get that thing up onto the screen. Now, to do that, we need to know where to put it, and that's where the coordinate system comes in. The PyGame coordinate system is old school. It's X increments across the screen, as one would expect, but unlike what you might expect, the Y coordinate increments down the screen. And the reason for this, as I say, it's old school. It's because of the way that video RAM was implemented in early computers. Well, it kind of still is now, but it's basically tied into video RAM, where to display things on the screen, the computer would poke into RAM, the video RAM, figure out what's there, and send that to a CRT. Okay, you're all looking at LCDs. Who knows what a CRT is? Good. So, I haven't seen a CRT in a very long time. So, CRTs scan across the screen, starting at the top, going down row by row. And it's basically just saying, what's in video RAM, put that up on the screen as it's scanning across. So, the Y, the height on the screen starts at the top. And that's just the start of the video RAM. That's just for convenience. So we still use that video refresh mechanism these days, but modern graphics systems like OpenGL are sensible enough to say, look, Y can start at the bottom like we expect. It's just PyGame starts at the top. So pretty much everything else has Y starting at the bottom, incrementing up. So, to draw that thing up on the screen, we need to know the coordinates. And the coordinates there are pretty much straight in the middle of the screen. So we'll say X is 320, Y is 240. So, to draw it, we need to load an image up off disk. Using PyGame image load, that'll load a variety of image formats. As I said, PNGs, JPEGs, Windows bitmaps, because why not? TIFFs, a variety of things. PNGs are good though because you don't get any noise introduced into your image. It's a lossless format. You can also load GIFs, but PNGs have the added bonus of having an alpha channel, which means that you can have images that nicely blend into whatever they're being drawn onto. So if your image does have an alpha channel and it does have a nice smooth blend, then it will be blended into the existing image on screen by PyGame just for you. It just does that. You can have transparency in GIFs, but it's not as pretty. You will end up with jaggies because it doesn't have an alpha channel. So we load up our image using PyGame image load. The first thing we do when we're down in our event loop, so in our main loop, is we fill the screen with a solid grey colour. So we're just clearing the screen. Then we do a thing called a blit, take our image and say, copy this up onto the screen at the coordinates 320 and 320 x 320 y 240, and then we flip the screen. And I'm going to come back to those some of the details of those commands in a moment. The first thing is the colour. So colours are specified as a 3-tuple of red, green and blue, and you can pull them straight out of drawing programs. There's websites that'll tell you these things. There's all manner of places. Eventually you just kind of, you make stuff up. But it's a number from 0 to 255, specifying the red and green and blue components of the colour. So, if you'd like to see that running, then 04 is the file to run. The next thing to talk about, Blit. So that, again, old school. SDL, which is what PyGame's built on, SDL's old. PyGame's old. As I said, it was mature in 2004. SDL is older, and hence, it has that coordinate system that's very much based on CRT video RAM. The term BLIT is actually an acronym for block image transfer, and it basically says it's an operation that was implemented in very early graphic systems. It was the only one we had, which basically took a bitmap and copied it to somewhere else. Block of image, transfer it. Blit. Could have been draw, but they went with Blit. Who had an Amiga? Anyone? No? There was actually the really cool thing about the Amiga, which was kind of far ahead of anything else that was kind of in the consumer space at the time, and one of the reasons why it was so successful was that it actually had a main processor and 2 coprocessors. One of those coprocessors was called the blitter. All it did was blit, copying images around. But that's something that basically meant that the CPU, which wasn't very powerful, it was an 8 megahertz 68,000 processor, it didn't have to do all that hard work of moving images around. The blitter could do it for you. You had to program the blitter, but it wasn't a complex thing. It also had a processor called a copper, which actually stood for coprocessor, but you could program it as well. You could actually set it up with sequences of commands to do other stuff, like invoke the blitter. So you could actually have your main processor write little programs for that processor, which did that process. It was really neat. It was very advanced for its time. Anyway, I digress. So the other thing that's weird in this is the last line, which is flip. And the reason we have that there is because we're doing our thing in our program, drawing stuff up on the screen. Meanwhile, the computer's doing its own thing. It's taking what's in the video RAM and drawing it up on screen. Okay, so we're drawing to video RAM, and then something else is taking the video RAM and drawing it up on screen, probably while we're drawing to video RAM. And if we're doing it at the same time, we end up with something called tearing. I don't know if you can see that, but in the middle of the screen here, as we're drawing our stuff on the screen, right about here, the computer has started drawing a different frame, a different version of the video RAM up onto the screen. Now, this probably won't work because modern computers have all sorts of workarounds for this stuff kind of hardwired into them. And don't run these examples if you're prone to issues with strobing. But if you'd like to give it a go, run 04-tearing. I'm pretty sure Macs won't work, but you can give it a try anyway. You should get, the screen should clear and show a bunch of flickering, all right? No, if it doesn't work, you'll just see a blank screen. It's completely black, yeah. Windows, yeah, that's what I get. It used to work. Anyone? No? No. Oh, that's a shame. Anyway, it's basically a little program that forces the tearing. And then the tearing fixed program fixes that. And it fixes it by using a thing called double buffering. Did that work?
That was on the fixed version.
Oh, the fixed will work. Yeah, that will absolutely work. The tearing one, unfortunately, yeah, it's harder these days to force it without resorting to invoking OpenGL. So the way around tearing is to use a thing called double buffering. And the idea with double buffering is that instead of having video RAM and we draw to video RAM while video RAM is being copied to the screen, we have two versions of video RAM. One of them we call our drawing buffer, and we draw our stuff to it. And we have a display buffer, which is what is being sent to the screen. When we're finished drawing, and we know that the computer is finished displaying, for now, finished using video RAM to display to the screen, we switch what the computer is sending to the screen to our drawing buffer. And we switch to using the display buffer to draw to. So we kind of switch them around. And so we're using two different buffers to do the two different tasks. And the flip command is what we use to do that flip. So once we know everything's done, we're finished with our drawing, the computer's finished sending everything to the screen for now, because it does it kind of constantly, we flip.
So does the flip command handle that timing?
Yeah, so the timing issue is that even though we're not using CRTs anymore, there's still a scanning process where the computer scans down through the video RAM and sends that out to the monitor because it's using a cable which is serial. So once it's finished doing that, there's a thing called a vertical sync, which is where it says, all right, I'm done and I'm going back to the top. And there's an event that happens in the system called a vertical sync event. And when that happens, PyGame gets that event and can say, okay, we're good to do a flip now.
So I mean, how do you know, especially with modern processors that are much faster, how do you know that you're not going to get ahead of the double buffering?
Again, PyGame manages that for you.
They won't let you draw.
Oh, no, you always have the draw buffer,
Okay.
but the flip might not happen immediately. Like, it might block for a moment. Very, very brief. But yeah.
So you will block until it's ready.
Yeah, but it should be a very brief amount of blocking. Okay, so sorry you don't get to see the coma-inducing flashing lights, but yeah, you get the basic idea from this image. Okay, so, oh, I've already talked through this. All right, so tearing, we avoid that, and we use flip to do it. So that takes care of dealing with the screen display issues and the tearing. One of the things that we need to be aware of is that our program is currently using a lot of CPU because it's just churning away, basically running as fast as it possibly can, even though we're not really updating the screen very often. In most games, we only need to update the screen about 30 times a second, but we are probably currently updating it 200, 300 times a second, even though there's not much going on. Eventually, we will have animation and such going on, but the basic idea is we need to slow our program down a little bit because it's unnecessarily churning up the CPU. We can use the PyGame clock command to do that, clock facility to do that. The clock facility, the clock object gives us a facility to just pause our program for long enough so that we slow it down to only being run every 30 times every second. What the tick function does, or tick method does, is it just does a little micro sleep for however long it needs to, because it records when it was last invoked. So it just makes sure that it doesn't get invoked more than 30 times per second. That's in the file 05, less CPU. So if you can probably just do a simple little comparison of the CPU usage there if you'd like to. But this is generally a good idea. Clock tick also provides us with timing information, which is quite useful, but we'll come back to that. An important thing to note is that this isn't going to take a slow game and make it any faster. This just limits the speed that the thing is running at down to 30 frames a second, rather than artificially, say, boosting it up to 30 frames a second. Yeah.
So it won't cut off processing?
No, because if you're processing, you're not calling this. Yeah.
Is it microseconds, the unit?
No, the number that's given there is the number of times it should be called per, it should be called per second.
Oh, time per second.
Yeah.
So if your processing takes more than 130 seconds, that's where you really start experiencing slowdown.
Yeah, your game will slow down. And obviously this command won't do anything. Yeah. It won't sleep at all. Okay, yep.
That's not asleep?
It's only asleep if it needs to. If you've come around really fast, then it'll sleep if it needs to slow the program down to that 30 frames per second rate.
So if the event comes in while it's sleeping, it'll interrupt it and allow you to process the event, or will it wait till it's done?
The event will just go in the queue. Yeah.
So it makes a slower game slower.
No, it won't slow a game down. If it's already below that threshold that you've set, then it won't do anything.
Because it'll be too busy processing the events.
Well, it won't need to slow things down. It doesn't need to reduce to slow the game down to that lower threshold. And it's actually an important point that, yeah, if events come in while it's doing that sleep, then they will be queued. And it does mean that, and I'll come back to this, but if the player is generating events particularly quickly, then you may miss, depending on how you handle the events, you may miss some. So if you're looking for, say, and again, I'll come back to this, but if you're looking for, say, them hitting a button to shoot, okay, and they're hitting it really quickly, then you may, if you're looking for the state of that key later, rather than looking for the actual key down events, then it may be that they've pressed it and released it while it was in that sleep.
But you said it was queued?
Sorry?
But you said while it's in sleep, the event is queued?
Yeah, the event is queued, and I'll come back to it. It's just something that, yeah, you have to be mindful of, that, yeah, there can be things happening in that sleep, but you won't get them until you actually invoke get after the sleep happens. Okay, so currently our game is quite, dull. There's not much going on. So let's introduce some animation. Let's move our little dude around the screen, or dudette. It's kind of hard to tell. To move something around the screen, all we need to do is change the location we're doing the blitting. And the simplest way to do that is to change our fixed 320,240 coordinates into a variable, or a couple of variables, and then modify one or both of them inside the loop. So if you run 06, the little stick figure should scoot off the screen. And if you don't quit, it'll just keep going. Okay, so, and another, yeah? So the coordinates are at the top left, yeah, and then it draws down. So something that's another important thing to understand is that when that stick figure disappears off the screen, we're still invoking blit. PyGame's not doing anything. Like, it'll say, oh, okay, you're drawing that, and it's off the screen. Oh, whatever. Doesn't do anything. Okay, it's not going to draw off into random memory somewhere and corrupt your system. It just does nothing. Okay, it says there's nothing to do. So it's okay to draw stuff off the screen, don't do it too much because there is a bit of a processing overhead of just invoking the blit method, but don't get too worked up about drawing stuff that's off the screen.
And what if your image is partly off the screen?
Well, you'll get the bit of it that's on the screen drawn, yeah. Something to experiment with is edit the file and move the fill command so that it's outside of the loop, or just delete it. See what happens. Should end up with what do you see? Hopefully something. If you delete the fill. The fill command, this one here. Yeah, delete that one. You just get a black screen. Oh, yeah. Oh, yeah, so sorry. Yeah, that's why we don't delete it, we move it. So just move it up to above the while statement. Sorry, yeah, that's why we don't delete it. I forgot that the image doesn't have a background. You see, you still need to do the fill just once. Okay, I can see that some people are getting that working. All right. So that's why we clear the screen every time. Now you should see it flickering. Oh, okay. So on some systems you'll see it flickering, on some you'll just get a solid thing because the double buffering is implemented slightly differently on some systems. Yeah. Yeah. So on some systems, the double buffering is actually implemented as a single buffer, which is kind of copied. But on other systems, it's actually two different buffers. So you'll actually see two different versions of it flickering. But you should basically see stick figure drawn multiple times across the screen, because when you don't clear it, you get the existing contents of the buffer. Okay, so another important thing to remember. All right, so that's basic animation. Let's make this kind of a game. Let's do some user input. So, user input, they come in as events in the PyGame event queue. And there's two ways of handling keyboard events. We can get the events out of the event queue, or we can look at the keyboard state. PyGame actually retains the state of each of the keys on the keyboard, whether or not they're pressed down or not. And again, this comes back to the issue around that micro sleep, that if the key is pressed and released during the micro sleep, the keyboard state will show that it's not held down, even though the player did actually press it quite quickly. Yeah, so PyGame manages that keyboard state for you because it's not very much fun to implement your own state management. So we're just going to use that keyboard state thing rather than using the event loop. So now instead of our just incrementing the X position, we're going to manage the X and the Y position based on the arrow keys on the keyboard. So the left, right, up, down are the symbols for the arrow keys in the PyGame keyboard. And get pressed just returns a dictionary, which has a Boolean state for each of the keys on the keyboard. Another thing to note with this bit of code is that we're using distinct if statements for each of the keys. So if the player is holding down a combination of keys, they'll combine. So if they're holding down left and right, there'll be no X change. Similarly with up and down. If they hold down left and up, you'll get both. Which is pretty much what the user would expect. Eventually, this code would have to get slightly fancier though, because the movement of the player's avatar will be at a different speed if they're holding down a single key as opposed to two keys in a diagonal. So there'll be 10 pixels per whatever if they're holding down one, or 20 if they're holding down two. So you would have to throw in some basic mathematics to combine those two and figure out the actual amount, x and y, based on the 10 unit length of a diagonal. Again, basic mathematics, not too hard. You will, sorry to say, need to revise your trigonometry eventually as a game developer. Yeah, so we're using the keyboard state thing here for these keys because the player is typically going to be holding them down for a long time. They're not going to be doing impulse pressing, like really fast pressing. We still use the event loop to look for the escape key because they'll hit that quickly, and we might miss it if we use the keyboard state. Other event types that we might want to handle in our event loop are the mouse ones. So mouse button down and up, just like key up and down, you get 2 events. The mouse motion for when they're just moving the mouse around. The buttons that you get in are attached to the event. So each of the different event types has a different set of attributes attached to them, and this is all in the PyGame docs. The little cheat sheet I've got there has, I think, some of them listed. I'm not sure. I think I added that. But anyway, it's in the PyGame docs what those things are. There's also a global that keeps track of the mouse position, so you don't have to look for these events. You can just ask, where is the mouse at the moment, and you can find that out. Another thing to note is that the scroll wheel, old school, it's implemented as mouse buttons 4 and 5. So like 4 is is scrolling up and 5 is scrolling down. Yeah, so yeah. Which is typically enough for most games. But again, something like Piglet, which is more modern, actually implements a floating point value of the amount that the scroll wheel was moved in both the X and the Y direction, because some mice have both axes. Okay, so that's mouse events. But again, our game doesn't have mouse input. We're not interested in that. Some of the other example code that I've got there does have mouse input, and you can look at those to see how that works. So the next thing we're going to do is clean up the way that we're drawing on the screen a little bit. Again, a little bit of software architecture. We're going to introduce a thing called a sprite. I'm honestly not sure where the term sprite comes from, but it's a very common term in graphics and game programming. And it encompasses the concept of a thing that's drawn on the screen at a certain position. So it retains its state of what it looks like and where it is on the screen. In PyGame terms, this means that it has an image attribute and a rect, which describes the size of the thing on screen. Which is the top left position and the dimensions of the image typically. Another nice thing about sprites is that we can have, because they're objects, and we can control their classes, you pretty much always have to subclass the sprite to add in the stuff that's interesting to your implementation. So we can add in the behavior, the mechanics, the game mechanics that are specific to each of the sprites. So the player sprite, well, that's a thing that handles the user input from the player. So we attach that to the sprite itself. Yeah, if we had a different sprite, which is, say, an enemy that's on screen, then it could have an update method that moved the enemy around and detected when it was, say, colliding with the player and would kill the player or hurt the player. So that we can nicely encapsulate that behavior, that information, with the thing that's actually being drawn on the screen, which is very clean. To get that drawn up on the screen, we have to change things around a little bit. First of all, the image, that's being managed by the sprite itself, so we don't have to load that in our main loop anymore. PyGame uses a concept of sprite groups to manage sprites because you always end up with a bunch of sprites. So it just says, look, we're just going to always include them in a group. So we create a Sprite group. This is the most basic type of group there is. There's about a dozen different types of PyGame Sprite groups that provide a bunch of different functionality, but this will do for most things, most games. We create our player and we attach it to the game object as an attribute. So anything else that has the game object can access the player. They can find out where the player is. So our enemy class, as long as it can access the game object, it can access the player, figure out where the player is to know whether it can kill them. Sprites.update, that's a method on the group. Groups are really nice. They basically delegate things down to the sprites. The basic group class, that's all it does, is it collects together sprites and it delegates calls to update and calls to draw. So it says, when the group update method is called, all of the sprites in that group, their update method is called, if they have one. And similarly with draw, when the draw is called on the group, it delegates that down to all of the sprites in the group and they're all drawn. I don't actually have the number here, but I think we're up to 6 in terms of the 8 sprites. Yeah. Yeah.
Sort of a question. I'm looking at that, I think it's at file 8, and I see that it has sprites update, and then right after it has screen.fill. Would there be any, where if you flip those lines?
It would make any difference. Update doesn't actually draw anything. It just does the game mechanics. And you do tend to have those as separate things. The drawing is just rendering things on the screen, just to keep things nice and separate. It's very much like the model view controller kind of idea of things, where you separate those concerns to keep them clear. What is up to drawing and what is up to updating the game mechanics. Keeps things clearer. Okay, and again, this won't actually change what's happening on screen. It's exactly the same behavior on screen, it's just that the architecture has been cleaned up a little bit. So the next thing we're going to do is we're going to make our game time cleaner. I'm going to see if I can come out with a better way of explaining that, but we'll see. So at the moment, our game is running at maximum of 30 frames a second, and when the player holds down the arrow key, we move the player by 10 pixels. If the game runs slower, we're still moving them at 10 pixels, it's just 10 pixels less frequently. If we're running down at 10 frames a second, we're moving at 10 pixels per, 100 pixels per second. If we're running at 30 frames a second, we're moving at 300 pixels per second. So that all gets a bit variable. So what we can do is we can fix up our game so that things run consistently, regardless of how quickly the game is being updated. And we can also make all of our movements and game mechanics actually dependent on time, so they can be more predictable. The clock tick gives us a handy facility for doing that. It returns the amount of time that's actually passed since the last time clock.tick was called, which it has to know anyway, because it has to know how much time it has to sleep for. So it returns the amount of time since the last time it was called. In our program, that'll be pretty darn consistent because we're going to be running at that maximum of 30 frames a second. Because PyGame's a little old school, as I've previously mentioned, that time comes back as milliseconds. So we divide that by 1,000 to get our seconds that have passed since the last call. One of the nice features of the PyGame groups, when they do that delegation of update down to all of their sprites, it'll pass all of the arguments you pass into it. Positional arguments, they all just get passed in. So your sprites should have that extra argument in their update method. So we're going to pass in that delta t, that change in time value. Sorry, dt. Is anybody not comfortable with the concept of delta as a thing? Yeah. So delta just means change. So we're talking about the change in time. So dt is just a shorthand that you tend to use in games. No, the DT is the amount of times that's passed since the last time clock.tick was called. So it's basically each time this loop runs, that amount of time, that tells you how long it took to run that loop. So then in our player update method, we can add in that DT argument because that's being passed down to us by the group. And then we can modify all of our movement values so that they are a pixels per second value, so 300 pixels per second. And then that'll be consistent regardless of how quickly the program is running. It'll be consistent regardless of what system you're running on. If you're running on a system that's not as capable, the player's avatar will still move at the same speed.
That means you have to have all your sprites of the same group having an update to make up that acceptability.
That's correct, yes. All of the sprites in that group have to have the same signature on their update method.
And what is 30 frame per second is kind of slow when you see the steps. So what is a good amount?
30 frames per second is pretty good for most things. You can go up to, like an action game will typically only go faster than that if it's what is called a twitch action game. So it has to respond very quickly to user input. Okay, otherwise, because you're generally speaking, human eye isn't going to be seeing much more fidelity beyond 30 frames per second. It depends on, and it can depend on the video hardware as well. Yeah. Yeah. But again, for most games, that 30 frames a second is what most games run at. But again, going up to 60 or so, if it's a game that has to do that rapid response to user input, and most like competitive first-person games will be running at that higher speed. Okay, so that's moving stuff around, so that's cool. And at this point, again, there's a bunch of games that are possible by moving something around. So let's talk a little bit about scene construction. So at the moment, we're just drawing one thing up on the screen. We can draw multiple things up on the screen, as we saw, if we don't clear it. But if we want to compose a scene with some background stuff and some foreground stuff, it's really easy. We just draw it in the order we want it to appear from back to front. So we'll start out with a fill, typically, which is kind of the sky color. We can draw in some background imagery. If the game is a scrolling game, where we're scrolling from side to side, then we might draw these in a couple of steps so that the stuff in the far distance moves at a different speed to the stuff in the foreground to give an impression of parallax. We can draw some foreground imagery over the top of that, so that might include the player character. And then over the top of that, we can draw an additional foreground imagery which overlays the existing foreground imagery. So in this case, the trees, which actually kind of poke down below the level of the ground is drawn over the top of them. So it's nice and clean. There might also be like foreground grass or something like that. Anything that the player walks behind would appear in that foreground. Does that mean morning tea's out? Is morning tea out? It is? Okay. I was kind of aiming for 10:30, but we'll see how we go. Okay, so we'll modify our little fledgling game to include a background image, which in this case is just a pretty straight gradient fill. But we just load that up, and instead of filling the screen with a flat grey colour, we draw that background image, which just happens to be the size of the screen, instead. And that handily clears the screen and gives us something slightly more interesting in the background. And then we draw our player over the top of that. So that concept of having the layers to to build up the scene. Okay. Oh, and that's in file 10. So let's... Okay, so as we're building up the game, we've already got some player controls in there. We've got the arrow keys. We could introduce events that happen outside of the player's control, things that are just straight timed events or triggered by interaction with things on the screen. And at some point, we're going to have to detect when the game is won or lost. So these are things that we'll start looking into implementing now to make it a more kind of well-rounded game. So first up, let's add some stuff for the player to interact with, some obstacles in the scene. Limit where the player can move, because at the moment you can move off the screen, which isn't very good. So to do obstacles, we need to handle collisions. And there's 4 common approaches to handling collisions in video games. 4 basic types that in pretty much most 2D games, and when you start getting into 3D games, they kind of just use an extension of these. The first, and by far the most common, is axis-aligned bounding boxes. This basically means that we take the image of the player and any of the obstacles, and we store a box around that image which is aligned with the X and Y axes of the game. So the bounds are always horizontal and vertical with the X and Y axes. If the image rotates, the box stays aligned with those axes. That's why it's axis-aligned bounding box. And the reason we keep those boxes aligned with the axes is it makes the code to check for collisions much, much simpler. If you rotate the box, it all becomes much more tricky. So to check for a collision, we just check to see whether the boxes are overlapping. And that's really, really easy. You compare the top against the bottom and the bottom against the top and the right. You're basically comparing opposites. And if they are all overlapping, then you've got a collision. The unfortunate thing about axis-aligned bounding boxes is that you can get a lot of false positives. So here you can see that the images clearly aren't overlapping, and the player would get quite grumpy because we think that they're dead. So the thing is, in fast-moving games, like this would be from an asteroid or something, player probably wouldn't even notice. If it's moving fast enough, they probably wouldn't even notice that, like, oh, look, I was close enough, I'm probably dead. So another thing you can do is have the bounding box not be fixed to the size of the image. So you can take the bounding box and just kind of reduce it down on the image. So there's a bit of overlap where the player's in kind of a safe space. And that can often produce slightly more fun results for the player because they can be a little bit more daring with how close they get to the obstacles that'll kill them. A variant on the bounding box is using a bounding circle. So this simplifies the collision code even further and gives the player even more freedom to get closer to obstacles, because depending on the shape of the obstacles. All we have to do is compare the distance between the midpoints of the circles, compare that to the radiuses of the circles, and see if they're overlapping. So the previous false positive that we had, the player is safe, and in this case now, they're clearly overlapping. The player wouldn't dispute that. Unfortunately, you can get false negatives, but again, being kind to the player sometimes is a good thing. And they probably wouldn't really notice, again, in a fast-moving game. The other nice thing about circle circle is that if the image is rotating, the collision box is still pretty close to accurate. Whereas if you used a bounding box, an axis-aligned bounding box, as the image rotates, the bounding box is going to grow quite significantly as the bounding coordinates of the image grow. So bounding boxes, bounding circles, pretty simple to implement. The next type of collision detection is called hash map, or in Python you just use a dictionary. But we take the axis-aligned bounding boxes of each of the things in the game, and we map them to cells which are several pixels in size, so probably about 10 pixels in size in this picture. And then we store those cells that each of the boxes occupies away in a dictionary. And then when we're checking for collisions, we simply have to look up those cell entries in the dictionary to see whether there's something there. If you have a game with a whole lot of stuff going on, so you have a whole lot of these rocks or a whole lot of bullets or whatever, then this is way faster than doing any of the other methods, because to check for bounding box collisions, for example, or even bounding circle collisions, you have to do a lot of loops of comparing object versus object. Whereas in this case, for each object, you're just doing a single lookup into the hash map to see whether it's colliding with something else once you've populated that hash map. There is one hash map for the game. Yeah. Yeah, and you can see in each of the cells, you can have multiple things occupying there. So if the player is shooting a stack of bullets, their bullets would go into the cells, and if there's enemies shooting a stack of bullets, then they would also go into the list for each of the cells. And then you're just looking in those cells to see what's in there. Who's familiar with the concept of bullet hell games? Yeah. All right, so bullet hell games are those like arcade games where basically all you can see on the screen is bullets, either yours or the enemies. And so in that game, you would use a hash map because it's the only way you're going to keep up with the processing load of detecting the collisions. The last type of collision detection you find in 2D games, and certainly not in 3D games, is pixel perfect collision detection. So I've blown these images up so you can see the pixels. So what you're doing in this type of collision detection is actually taking each of the pixels in the ship one by one and seeing if on screen there's a pixel from something else. This is really slow and expensive. And in most games, it's complete overkill. And oddly enough, it's the first thing most people do when they write a video game. So don't do it. There are some games that work when they use pixel perfect collision detection. Who's familiar with Worms? Yeah? So it's all about pixels. But in action games, you don't need it, and it will just slow things down, and it's overkill. So what we're going to do is we're going to add some obstacles into our silly little game. What this code does is it just loads up a new image called a block, and it places a block all the way around the edge of the screen, just as a solid wall around each of the sides of the screen. We'll create a new group for the walls so that they're separate from the player, just for convenience for looking up those walls. We can just iterate through all of the sprites in that group to find all of the wall objects. Okay, and we're storing the walls away on the game object so that we can look them up later on if we need to. Yeah.
Probably a question. Is there why 32?
32. So we're stepping by 32 here because the block image is 32 pixels by 32 pixels. Sorry, yep. So each step across the screen, we're adding a new image. And then the funny statement here is basically that's doing the sides. So yeah, a solid line at the top, a solid line at the bottom, otherwise just one on each side. Yes, so we've got our group, which has all of those blocks for the walls, and we've stored it away on the game. So then when we, so now that we've got some interesting information on the game object, we're extending our update method to include the game object so that when the player update happens, we can access the game, the state of the game, including those walls, so that the player can run into the walls when the player is moving around. So we add the game to the update method. And in the process of doing our collision, if the player does collide with the wall, we want to basically not move them. So what we're going to do is we're going to record the current position of the player. We'll let them do all their key handling update stuff and move them. And then we'll see if they are colliding with the wall. And if they are, we just reset the position to where they were before we did the movement. It's definitely, this is the simplest and trivial, most trivial way of doing the collision with walls. PyGame provides us a handy little method called Sprite collide, which basically says take this sprite and see whether it collides with anything in this sprite group. That's why we stored all of our walls in a separate sprite group. So we're colliding self, which is the player sprite, with the sprites in the walls group. We're passing false because the default behavior of PyGame Sprite Collide is to kill any sprites that are collided with. So that would actually remove those wall blocks from the game, which we don't want to do. So we pass the false value in for the do-kill parameter. It's actually called do-kill. And if we get any results there, then we reset the player position to the last position. So you can see that in 11. Should be able to see walls and should be able to run into the walls. Yeah?
What is the collision method that they're using? Is that the axis?
Oh, that's just straight axis aligned bounding box using the rect parameters. It's a good question. Yes, yes you can. Yes, there's a few others in the Sprite module. Okay, so that's pretty basic stuff. You'll probably see if you muck around with it and you kind of push the edges of it that there's some odd behaviors where you can kind of get a little bit stuck on the wall. And you also might notice that as you run into the wall, you kind of stop a little way away from the wall. Yeah. So that's because we're doing this very, very basic resetting of the position if they get too close. So what we want to do is modify our approach so we use what's called conforming collisions, where we move the player as close as they can get to the wall when they collide with the wall. So, unfortunately, that makes our collision response a little bit more complex. What this is doing is basically saying, well, we need to figure out which side of the block they're colliding with, so we know which side of the block to place the player against. So if they're colliding with the left side of the block, if they would have gone through the left side of the block, we want to place the player up against the left side of the block. And similarly with all the other sides. So, for example, this one here is saying if they were previously away from the left side of the block, and then they cross the left side of the block, then we want to place them on we want to place the right-hand side of the player against the left side of the block. Fortunately, yeah, so the rect objects in PyGame have a stack of these handy little attributes that you can look at and assign to move move objects around, move sprites around. So you can assign and look at the left and the right and the top and the bottom. There's center attributes and other things like that as well. Very convenient. And yeah, we just do that for each of the sides. So now, if you run 12, you should be able to go right up against the walls.
Wouldn't that make more sense to set the track equals new and then change new? Because here, I mean, the new equals set the track and change it. So it's probably mutable type, so we can actually change it, but it's kind of weird. It's like this local variable new that is going to.
I assign that to a variable simply because having self-rect whatever in there kind of just pushes the code out. That's the only reason why new's there.
Yeah.
Yeah, it's not taking a copy of anything. It's the same object.
Yeah.
Yeah.
I know.
It's to make the code prettier.
Yeah.
Is that, you're okay with that?
Yeah, it's just, it's okay.
Yeah? All right.
So for cell in PyGame Sprite collide returns every sprite that's colliding, or just the player sprite that's colliding?
It's every sprite in the walls group that the player sprite is colliding with. So when you're calling sprite collide, you're passing a single sprite which you want to check against a group of sprites. And it'll return a list of all of the sprites in that group that that single sprite is colliding with. And indeed, in this example, you could be, if you're on the boundary between a couple and you move across, then you could be colliding with multiple. And in fact, you'll see if you do run up against the side of the, run up against a wall and try to move along the wall, you should run into problems. It won't let you move along the wall very far, or at all, possibly. But we'll come back to that. We'll make the game slightly more fun before we come back to that. What we're going to do is introduce gravity, because gravity is fun. Gravity improves games. And it's really easy to add in. So we need a couple of extra variables. These are kind of around the wrong way. So the first thing we need to know is how fast the player is moving vertically. So the delta y value. That's what dy is, not direction y, it's delta y, it's the change in y. So it's the amount of y that we're going to add on to the player's position every time we update, based on time. We also store a flag called resting, just so that we know when the player has stopped moving, they're actually resting on top of something in the game, because that's convenient to know. And the reason the resting is convenient to know is we need to know when they can jump, because the player can't jump when they're in midair. Not in this game. In other games they can, but not in this game. So we get rid of the up and down key handling because they can't just fly. Not in this game, not yet. And we change it to say, look, if they're resting on the top of something, they can hit the space bar and that'll jump. And we handle jumping by just giving them an impulse, a single one-off setting of their change in y to minus 500. Now it's minus 500 because y increments down, so if we want to make them jump up, we have to say minus. Minus 500, just a number. You know, you might want to make gravity stronger or their jump more potent, but in this particular game, 500 works pretty well. And that'll be setting their vertical speed to 500 pixels per second vertically. We then apply gravity at a rate of 40 pixels per second. That should technically be a rate per second, but I'm being a bit lazy here. This is good enough. We limit the vertical speed down to 400 pixels per second. It's important to limit speeds in games because if you go too fast, your collision detection might end up skipping walls where it should actually be colliding with walls. If you move it faster than 32 pixels per second, 32 pixels per update, sorry, not 32 pixels per second, 32 pixels per update, which is like roughly 900 pixels per second, then you've got a very good chance of missing a collision with something that should actually be collided with in this particular game. So, yes, so if the space is hit, we do that 500 pixels per second jump impulse. We apply gravity at a rate of 40 pixels per second, or 40 pixels per update per second. And we limit that vertical speed to 400 down. And then we update the Y position as previously using that delta Y instead of a fixed value from the keyboard. The other thing about the resting flag is that we need to set it to whatever it should be. And we set it in our collision response code. So if the player is colliding with either the bottom of a block or the top of a block, we have to say, we have to modify their vertical speed. So if they've jumped up into a block, we have to set their vertical speed to 0. And if they land down onto a block, then we need to set their vertical speed to 0, but also set the resting flag so they can jump again. And if you run 13, you'll see gravity in action. And we'll demonstrate the reason why we set the vertical speed to 0 later, because some people forget to do that, and you get a strange side effect. Yeah.
I see in the gravity one, you can jump left and right, but you can't move very far left.
Yeah, we'll come to that. That's a peculiarity of the current implementation that we'll clear up. Yep. It should have, in the previous version, you should have still had a problem moving along walls. If you ran down into a wall and tried to move along it, you should still have a problem moving along it. Oh yeah, if you don't run the conforming one, then you'll be separated from the wall a little bit. So it's 10:30, so let's have a break for morning tea before we get on to some other things. How does a 10-minute break sound? Yeah? All right. Okie dokie. So we've got gravity, which, as I said, improves every game. Now, the other thing, well, the thing you might have noticed about the game at this point, though, is that it's kind of a constrained playing area, which can work for some games. But I think we should make the game bigger. So let's talk about how we do that. Okay, scrolling things around. I don't know why that says aside. Yeah. Okay, so given that we have a large playing area, which we'll say is the grey box, okay, and we have a view onto that large playing area, which is the size of the screen, okay, the white box there is basically how much of the playing area that you can display at any one time. We position that view in the total box by some X and Y position. Okay, so that represents us moving the screen around inside the playing area. The way we do that in actual practice in our code is that we change a draw method, which would previously just blit the image that we want to draw onto a screen, so the player sprite, the walls, everything in the game. We change that from blitting its image at its position to modify the blitting position to include the view position. And we subtract the view X and the view Y from the thing's position to get the actual position that we draw it on screen. Now, remembering that if we draw stuff, if that means we end up drawing stuff off screen, doesn't matter. PyGame's not going to fall about laughing. You're not going to crash your computer. You're not going to do any significant extra processing. It's just going to not display it on the screen. It's going to be drawn somewhere else. Or not drawn somewhere else. So scrolling the viewport around, actually not that hard at all. You just have to subtract that position information, the X and the Y position. That's something that can catch people up, that can stump people for a little while. So there you go. So actually, the aside is actually supposed to say aside, Flappy Bird. So if you'd like to look in the example code, there's a directory called Flappy. And it's a thing that I threw together in, not kidding, about 40 minutes, including the creation of the graphics, which you'll see are quite awesome. And if you run Flappy, that's a very simple example of a scrolling game. You hit space is the one button for that one. And it's okay if you suck at it, because I do too. And it really did take me a total of about 40 minutes to write and create the graphics for it. The graphics are awesome. Has everyone found it? It's all good? It's in the directory called Flappy, and it's called Flappy, so just Python Flappy. I can't remember. I'm pretty sure I am. Anyway, so Flappy is stupid. And if you, it is such a trivial game. If you have a look at the code, you'll see that there's a sprite for the bird. And the viewport stuff is just, there's a position. I call it distance. And that's just, that's used in the sprite draw to, in all of the sprite draws to change where stuff is drawn. And that's how we scroll the view. Oh, there's no clock. Oh, that was lazy of me, wasn't it? Anyway, okay, so that's another 5 minutes of development time I needed to put in there. Oh my God. Okay, so that's scrolling. So what we'll do is we'll add scrolling to our platform game. So, to add scrolling, yes, so we need to incorporate this view information into, this is the source from Flappy. So where is it? The camera X. Yeah, so we store that camera X. Is this the source from Flappy? No, because it's got a clock. Oh no, this is the slightly modified version of the platformer that I don't think I actually included. Oh no, I did. Yeah, 13B. Yeah. So that'll show you the scrolling. So we're just keeping a single one of those two potential viewport positioning things, just the camera X rather than camera X and camera Y, just to keep things slightly simpler. And again, to move the viewport around, all we do is subtract that X position that the viewport is at from everything we're drawing. And by subtracting that position, we're shifting everything off to the left that needs to scroll off to the left. All right? And we encapsulate that scrolling behavior in a new Sprite group. We can subclass the Sprite group, just like we subclass Sprite, to encapsulate that camera position behavior so that when we invoke its draw, instead of doing the old thing of rendering each of the sprites at its position, we render each of the sprites at its position minus the camera. So it's nicely encapsulating that. Okay. Oh yeah, and we also extend the world. That's not very interesting though. We're just bumping up the X size of the world. Yeah, so now you know enough to write Flappy Bird. Well done. You can now make your millions. What we're going to do though is we're going to introduce a proper map to play in. All right, so currently we're just drawing those walls around the game. Not very interesting. So now we're going to introduce something a little bit more complex, a thing called tile mapping. And we're going to use a common format, file format called TMX. Not sure what that stands for, anyway. But it's a very common tile map format. It's tile map XML, of course. It's XML, by the way. So because we're not insane, we're going to use a library. Because I'm insane, I wrote the library. There's a whole bunch of TMX libraries out there, but they all sucked, so I wrote my own. Tile maps are pretty straightforward. This is a tile map. It's just a grid. It's empty, but it's a tile map. Tile maps are just arrays, and they have cells, and as I say, this one's blank. So we have cells. Each cell in our tile map is 32 pixels in dimension, X and Y. And if they're empty, we'll see the background, which is grey, not very interesting. Cells can have contents, which are called tiles. So we have a tile set, which is an image we keep somewhere else, and it has a bunch of different images inside it, 32 pixels by 32 pixels. There's a line separating each of these, which wouldn't actually be in the tile set image, but it happens to be in this because I took a screenshot of a tile map editor and it adds that border, but the actual tile set does not have that border between the images. Sorry about that. But the nice thing about tile mapping is that we can take one of these tiles and copy it up multiple times on the screen, so we can have this humongous playing area made up of just a few small images. Very efficient. Oh, I've got the Mario thing. I'll show you the Mario thing if we've got time. Okay, so the key thing here is efficiency. Okay, we've got a very small number of images that we're using as our source in memory, and we're making a very large picture out of those components. Now, to do this tile mapping, we're going to use an editor which is called tiled, and you get it from mapeditor.org, and it looks like this. So here you can see, I've actually got a couple of tile maps open at the moment in here. We've got our tile map area, which is the actual playing area that we're creating. We've got some layers, we'll get back to that, and we've got a tile set down here, which again, it adds that border thing between the tiles. And I'll come back to how we create the tile sets in a little bit too. The tile map can be really big. This is the entire map, it's 50 by 50 cells. The player obviously only sees a very limited view on that map, and we call that a viewport. And so that's kind of what we'll end up seeing on our 640 by 480 window. That's what appears in that window, just that little section. Our tile map has two layers. There's a visible layer, and an invisible layer which has triggers in it. Triggers are what implement our gameplay mechanics. So things like stuff that the player can run into. A special trigger which indicates where the player starts in the game when the level is created. The shapes that are created in this layer can have properties attached to them. So the P cell there that has the property player start, the red areas have the property blocker, meaning basically the player shouldn't be able to pass through those areas. And in the editor, they're just edited using a properties editor. You right-click on the thing you want to that you want to edit, and there's the properties. So this is the player property that's been set on the P tile. So to use this tile mapping library, we import TMX, we delete a bunch of code. Okay, so this is all of the code that we've used to set up the player sprite and the walls. And we replace it with loading the tile map from map.tmx. Actually, I think this is actually out of date. I think that should be a slightly different file name in the actual example code that you've got on disk. But anyway, we give it a TMX file name to load. When it's loaded, we tell it how big the viewport is going to be that we're going to be rendering. The TMX library provides its own sprite groups because it needs to order things and arrange things and display things in that viewport which it manages. So we're switching from using the basic sprite groups from PyGame to a subclass which has been provided by the TMX library.
Your TMX library, was it generated from a GUI or did you do it by hand?
So the TMX library?
The TMX map.
Oh, the TMX map was, I created that in tiled, the editor, yeah.
So you exported it as a...
Well, the save file format is just an XML, yeah. And in fact, if you look in the XML file, you'll see that the actual map information itself is I think it's base64 encoded zlib compressed data, or gz, because it's, rather than storing individual XML tags for every single cell, it's just more efficient. Anywho, where was I? Right, so we're basically just, this is just using the library to load the information. The tile map that we get back in the tile map object, it has layer objects for each of the layers that we've had in the editor. So there's that visible layer, and there's also the triggers layer, which in the editor I've called triggers, and the visible layer is called, I forget what it's called. It doesn't matter what it's called. But the trigger layer is where we've got the player start position. And we can search that using find to find the cell that has the player property set on it. And that'll tell us where to place the player sprite to start off with. So the player sprite is unchanged. We're still using the same implementation of the player sprite. It's just that it's added to one of these TMX layers, so that when the TMX library is scrolling the viewport around, it's also scrolling the player sprite around. So it's looking after all of that stuff for us, because all that stuff becomes a bit tedious to look after. If we've got a library to do it, we might as well use the library to do it. So then, and this is again just some housekeeping to change from using the existing sprite groups that we had to using the new sprite groups that we have that are provided by the tile map. So the tile map will do its delegation of the update method and the draw method just like the sprite groups from PyGame, the basic sprite groups. Okay, and some more housekeeping. We now have an explicit location argument that has been passed in to tell us where the player starts. So we have to handle that. And finally, to figure out what we're colliding with, instead of colliding with all of the stuff in the walls group, we ask TMX to tell us what are all of the blocker objects in the triggers map, in the triggers layer. And then we collide with all of those instead. The TMX layer actually has a collide method that it provides, which is very much like the Sprite collide, except it doesn't have the on by default do kill. It doesn't remove stuff from the triggers layer. And the last thing we do is we set the focus of the viewport, which basically says we would like the viewport to be looking at the player. And it does some intelligent stuff about making sure that by default, it will limit the movement of the viewport so that it shows the map and doesn't show stuff off of the map. So if the player is right down in the bottom left of the map, it isn't showing stuff that's off the map. And you can turn that off if you want to. Okay, so that is in 14 tilemap. And so now you should be able to jump around in an actual map. Yeah. Sorry? Okay, so the way that we're now doing collision detection, I'll jump back. Okay, so where previously the walls were made up of individual blocks, what would happen is that the player object would come up and collide against the side, sure, but as you tried to move against the wall, or even walk along the floor, you'd be colliding down, and that would mean that you're then colliding with the sides of the adjacent blocks, and that would prevent you moving side to side, or if you're pushing up against the side of the wall, moving up and down. So because we're not using those individual blocks anymore, we've just got a single large block, there's no sides in there to collide with anymore. Are we okay with that explanation?
So the same question as before, can we change the collision scheme? Instead of blocks, can we circles or circles?
Oh, sure. You could mix in. This is just one of the shapes that you could put in there. You could put in other shapes. The TMX library that I've written doesn't handle those yet, but you could add it in. Yeah. Okay. So yeah, that has now solved our problem of getting stuck on the walls. Okay. So that's really cool. One of the problems is, though, that we can't jump up onto the platforms from underneath, which is something that's pretty neat to be able to do. Okay, you just kind of bump up against them if you jump up. So it'd be really nice if we could jump up through platforms onto them. That's kind of fun. And common to have in platform games. So we're going to add an additional attribute onto our trigger layer objects to indicate that the sides of the boxes that are to be collided with. So these are labels, they're not actually information, they're just labels that you can add on, and I'll show you the interface for it in a second. But what we're basically saying is these kinds of blocks, you collide with all the sides, and these kind of blocks, you only collide with the top. And if the player collides with the bottom, we just ignore it, and so they can jump up onto the platform. And so in the editor, it looks like this. So the stuff with the label of TLRB, instead of just having a thing that's saying, I'm a blocker, we say the blockers are TLRB for top, left, right, and bottom. And for platform, we just say the blocker is T. So we only have the top blocker. And then in our collision detection code, we check to see which of those characters, T, L, R, and B, are set when we're checking for the sides that we're checking collisions. And so for the platforms, we only do the top test. We don't do any of the left, right, and bottom tests. Wherever bottom is. Yeah, it's down there. Okay, so if you run 15, you should now be able to jump up onto platforms.
Wouldn't it be simpler if the collide
Well, if it was a generic enough thing, yeah. It's not really, like, there's a lot of different uses for tile maps, so it's not really a generic sort of thing. You know, some platform games might not have, you know, the ability to jump up through platforms. So. There are definitely varieties of ways of handling it. This is just how I did. Yeah. Yeah. This is also how you would implement things like ladders. So if you have a ladder in your game, you need to be able to climb up onto a platform. You need to be able to make sure the player doesn't collide with the bottom of the platform as they're climbing up. So that's another one that gets people. Okay, so we have a burgeoning platform game, and it's becoming awesome because we can jump around in an actual world. By the way, the art that you're seeing there, I made that, and it took me like an hour, and I'll show you how. It's really easy. There's a really cool tool to do it. Let's add some enemies. Okay, so where are they? We don't have any yet. We need to add some enemies. We need to know what their basic behavior is, right? In platform games like this, your basic enemy behavior is just moving from point A to point B continuously. So maybe they might do something else. In our game, they're not going to. They're just going to move around. So to do that, we need to add some more information to our trigger map. Now, the generic term trigger is basically, it triggers for game mechanics. It's not like trigger, when you run over this, something's going to happen. The triggers are for your game implementation to say there's something needs to happen on the map here or whatever. So these triggers are basically saying we need to make an enemy here and here and here and over there. And we have some other triggers which are basically just reverses. So the basic enemy behavior we're having is that this guy is going to go, I think, right to start off with. As soon as that the sprite of the enemy collides with the reverser, we change direction. And it comes back and reverses direction. And that's all they do. And that there is Super Mario Brothers. So really simple stuff. So on the general idea of triggers, and again, triggers can do all sorts of things. Side-scrolling shoot-em-ups, okay, where you have a play area and a viewport and a player. Okay, I kind of cheated on the graphics here a little bit, but you get the idea. Okay, so we've got a red viewport and it's moving along the playing area, okay, so they're moving along. In the trigger map, we'll have enemy triggers, and when the viewport exposes those triggers, so we can say in our game mechanics, what triggers is the game currently, what triggers in the trigger map is the viewport currently colliding with? And in this case, none, and suddenly there is one. Okay, so we've collided the viewport with an enemy trigger. We can remove that trigger from the trigger map and create an enemy. And that's how scrolling games work. They're just moving the viewport along, hitting triggers, creating enemies, or generating other events. There might be other events. Sound effects, music. In the good old days, the music would be part, in some games, the music would be part of the map. And it would be playing as the viewport is scrolling, and that plays the game music. Okay, so we've created an enemy, and we can shoot them. Pew, pew. And there's an example of this in the directory there called scrolling something or other. Shoot 'em up. Something about scrolling and shooting. I forget what the name is. Anyone? Side scroller, yes. I knew it had scrolling or shooting in it somewhere. Anyway, so that's a very basic implementation of a side-scrolling shooter. Okay. So yeah, these triggers, they can do all sorts of things. Okay, so now we need an enemy. Bit of a code dump. We need a new class for the enemies. All right, there's a whole lot of stuff going on here. But some of it's very similar to the player, which we've already done. So we've got an image that we've got to represent the enemy. There's only one of those, so we might as well add it as a class attribute. The enemies are spawned at different locations based on that trigger map, so their location is going to be passed in just like the player. We need to record what direction they're going, and we'll just say that's the direction in X. I probably should have called that DX, but I don't know why I didn't. But anyway, that's the direction that we're going to move the sprite in, either 1 or -1. Oh, that's why I didn't call it DX, because it's not actually the DX, it's just a direction multiplied by 100. We could have said 200, -100. I don't know, I'm blathering. Anyway, so the update for the enemy, as I said, is really simple. We move them in a direction until they hit one of those reverser triggers in the trigger map, and we change their direction. And again, depending on whether the direction is one way or the other, we switch them around. We also conform the enemy rect to the trigger that it's collided with, so that it doesn't collide with it immediately the next update. So there's a just in case, because otherwise they can kind of get stuck on a trigger, depending on the amount of time that's passed since the last update. And then right down the bottom here, we collide each of the enemies in their updates, we collide them with the player. And if we've collided with the player, then the player's dead. We add them. We could also change that to hurt the player, but really, this is hardcore. So to add them to the game, we create another TMX sprite layer. We create a new layer so that we've got the enemies in their own layer, just for convenient organizing of things. And then for each of the enemy triggers we find in the map, we create an enemy at that location, and away we go. The last thing we need to do is set the isDead flag. Start off at false, and in our game loop right at the end, if the flag is true, the player's dead, and we just exit. Not very elegant, but it'll do for now. Important gameplay mechanics: start with something that works, improve on it later, iterate. Just like I've been doing all this morning, is just iterating. If you run 16 enemies, you'll see that in action. And you should die if you run into one of them. Because we're hardcore, no health bars here. Excellent. It's not that hard to dodge them. It shouldn't be. Okay. So it's not really a fair game at the moment. So what we'll do is we'll add, the ability for the player to fight back. The first thing we need to know is which way the player is pointing. Otherwise, we won't know which way to make them shoot. So we're going to change our player. We're going to ramp it up and add in 2 images for the player. Instead of just a single stick figure, we're going to have the player facing left or the player facing right. Blah, 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 blah. Yeah, so now we need to know which way the player is facing as well. So we have a direction flag there as well. And notice how sprites, they have an image and a rect, and they can have any number of other attributes, including other images, which are just ignored. The image attribute is the one that's actually rendered for the player, or the sprite in this case. But we can store other images, and then we can just flip them in and out, depending on which one we want to actually display for the player, which we'll get to in a moment. I don't need to do that. So now, when we're handling the key presses, or the state of the keyboard to know, to do the movement, we also set the direction and the appropriate image for the direction that the player is moving. And if you run 17, you'll see when you hit the left and right, the player image just changes because we've changed the image for that sprite. So what we've got there is very basic image animation, which is all it is changing the image that's displayed on the screen over time, or position on the screen, but also what the image is over time. Very, very basic animation here. Of course, we could get slightly fancier and introduce some actual movement animation. This is movements. This is from a classic book called How to Animate. And it's kind of the core textbook for animators, has been for decades. This is just one page from it, obviously. And this is online, you can Google image search this. And it shows the basic movements for cartoonish style movement. And you can use this to base your own artwork off to do character animation. And there's samples and tutorials for doing this out on the interwebs, YouTube videos. DeviantArt has so many tutorials for how to do pixel art and how to do character animation. You're spoiled for choice. This is a pretty crappy walk animation that I did a few years back now, before I found those reference animations. But still, this worked. And the game that this was in was pretty cool, I thought, anyway. So there's a couple of things when you're creating animations like this. So first, make life easy for yourself. Make all the frames, the images for the animation, make all the image frames the same size. Don't have your animation made up of images of different sizes, because otherwise you've got all sorts of other positioning information you've got to worry about. And also, make sure you account for frame rate. So don't just update the image on the sprite every n updates. You update it every n frames or every n seconds. Keep track of the time that's passed rather than the number of updates that's passed. Very much like before we were using the DT value, you just keep track of that. You accumulate that and then you flip a new image. And so you can use updating images to do special effects. This is a blast sheet of 16 images generated by a program that generates explosion sheets. It's online, there's a website. I've actually lost the URL, but it's not hard to find in Google. And again, you're just skimming through these images quite quickly in this case to display them one at a time. Pretty easy stuff. Just to update that image attribute on the sprite. Okay, so back to shooting. So we've got a player and we know which way the player is facing. So now we need to create some bullets. So we need to know where the bullet is going to start off its life. We need to know how long the bullet's going to live for, because we don't want it to just continue on forever if it doesn't hit something. Otherwise, we'll end up with a lot of bullets in memory. And we also need to have a delay before the player can shoot again, because otherwise they'll just spam bullets, and that's called a cooldown. Okay, so now we have another sprite class. Some of this, again, very similar to previous sprite classes we've had. The image class attribute, very much like we had in the enemy sprite, because there's one image for this class of sprites. We're passing in a location, but we're also passing in a direction, because when the bullet is created, it's created traveling in a particular direction. So we might as well pass it in and code it into that object when it's created. And we give it a lifespan, and we'll tick that down as time passes, and then we'll kill the bullet when its lifespan runs out. So in its update, and again, passing in the DT, so we know how much time has passed, and passing in the game object, so it knows it can access the stuff in the game, particularly the player, or the enemies, to see whether it's collided with any of them. And so we tick down its lifespan, and if that's gone below 0, we kill it with self.kill, and that removes the sprite from the game. All of the memory management, all that stuff, all handled for you. It just removes it from the game, and we return because it's done. Otherwise, we move the bullet at 400 pixels per second in whatever direction it was traveling in, either 1 or -1. And then we collide it with the enemies. Standard sprite collide. The enemies group that's come from TMX. It's a Sprite layer, but as I said, it's got the standard PyGame Sprite group interface, so you can just collide the bullet with those enemies. And we pass true because we want to remove the enemy from the game if it does collide with one. And if it does collide, then we want to kill the bullet as well, because it's not fair to have the bullet go through all of the enemies. Or maybe you have something that does, and you can remove that. We also have that gun cooldown, so that the player can't just spam bullets into the game. We start off with 0 because there's no, by default, at the start of the game, the player can shoot. And then when they do shoot, which I've bound to the left shift key because it's nice and big, it certainly is on my keyboard, we check that cooldown, and if it's 0, then they can shoot. We figure out which way the player is facing, and we create a bullet traveling in that direction at the midpoint of the sprite, which is about where the gun is on that image, at the midpoint of the sprite on the left or the right. And again, that's one of those many convenience attributes that PyGame's rect gives us as handy positions around the rectangle. And we set the cooldown to 1, which will be 1 second before the player can shoot again. And the gun cooldown is then decremented by the amount of time that's passed with a limit at 0. So we'll stop when we hit 0 using max. So if you run 18, you should now be able to fight back. Okay, so we're getting close to having a full game here. You didn't die. Seriously? Okay. Okay, so we're getting really close to a full game. What we need to do is add a little bit of polish, and then we've got something that's, pretty good. Could be up there vying with Flappy Bird. So we're going to add some sound effects. Sound in PyGame is really easy, assuming you have the sounds already. But we'll come to that. All you have to do is load the thing up off disk, and then you just say play. Okay? There's 2 different kinds of music. 2 different kinds of sound effects, sounds that you can play in PyGame. There's a concept of sound effects that you play, and they just kind of play once and short. And there's also, you can queue up music to play in the background behind everything else. I don't actually have music in this game, but it's pretty straightforward. The PyGame mixer documentation is very clear on it. So loading up the sound effects, you can use WAV files, or you can use MP3s or OGG Vorbis files. I just use WAV files because that's what the tool I use to generate the files generates. And I've got 3 different sound effects. These are loaded up on the game object itself because each level in your game might have a different variety of sound effects that are loaded up. I don't know. Somebody just tried it out. Yes, so you load those objects up, which is very much like the PyGame image load. It's PyGame mixer sound, not load, but who cares? Consistency, be damned. And then when you want to play the sound effect, you call .play on that sound effect. And the PyGame mixer has a bazillion channels. It can play, I think it's like 16 sound effects simultaneously, or mix them together, 32 maybe on some systems, I don't know. Anyway, so it mixes them all together. And so you don't have to worry about it. You just say play on the sound effects you want to play, and they'll be played. And so when, what we've got an explosion for when you shoot an enemy, you've got a shoot sound effect for when the gun fires, and a jump sound effect for when the player jumps. Look, I'm just going to let you guys, I forget, was it 19? If you play 19, you'll get the sound effects. I won't do it through the thing. Yeah, it'll be easy. I don't have to switch out then. So, fear the awesome, awesome sound effects. Excellent. Okay, so those sound effects are generated by this awesome tool called Sound Effectser, or SFXer. This is actually a tool. This is actually a port of it called CFXer, which is a port for Mac. There's a website you can go to. I forget what it is, but you can actually generate them like through the web. Oh no, I am going to do this because this is fun. Let me just pop out. Whoa. Thank you. No, you don't need to know about that. All right, so where are we? CFXer. There we are. This is CFXer. So it's a pretty straightforward interface. If you want a pickup sound effect, you click the pickup sound effect. Sounding? Oh, sorry. There we go. Yeah, so standard 8-bit platform game sound effect generator. Laser shooting. Explosions. Jumping. And so on. Random. And you can muck around with the sounds, the various parameters of the sounds to kind of tweak them. I don't know what half these things do. I used to know because they're basically the same sound parameters that controlled the sound interface device or SID chip in the Commodore 64. And that's what we're basically emulating the SID chip in a Commodore 64 to generate these sound effects. And when you've got one you like, so you like this, I don't know, one of these, you hit export and it generates a WAV file. And you play the WAV file in your game and away you go. Oh, here we are, we can... you could play with this for hours. Anyway, so really, really easy way of generating some fun sound effects for your game without having to go through a whole lot of pain of searching the interwebs for free stuff that's actually free and you're allowed to use, that hasn't just been ripped from some game without their permission, and all that jazz. So yeah, really, really fun little tool. All right. SFXer or CFXer. Okay, so sound effects. So some other things that we could add to the game, which we're not going to, is a counter for the number of lives the player's got, the number of lives you've taken away from them. Some screen maybe to show if they've won or lost the game, rather than just dumping them out to the console and saying you died. And, menus and opening screens and stuff like that. I'm going to show you a little quick example of how to handle scenes, but there's a whole lot of extra stuff around the basic game that you can add. It's what you add when you're done making the game. Okay, so once you're happy that you've actually got a game that is fun, then you can add all the other stuff. And it's very much like the sound effects as well. The sound and music and things like that. They can add something to the game, but if the game isn't fun, they're not going to add anything. Okay, so scenes. I've already kind of talked about this, where if you have multiple implementations of that game class, you can have one that launches another if you're going from one level to another, or you can progress between levels, just by having different implementations of them. And once you launch into each of those classes, their main loop, they're handling the events, they're running the show. So I've got another third-party module here called KesMenu. This is actually implemented in the 20 file, which it provides a very, very basic menu facility for a PyGame game. And so, yeah, I've got a menu item for play and a menu item for quit. And you can see that, yeah. So you can see it's got its own event loop where it's doing, the menu update has its own handling of the PyGame events to do whatever it needs to do in terms of selecting things and so forth, and its own drawing and everything. And its event handling is based on the options you provide for the menu items. So you provide some text and then something to do when that item is invoked. So you can see that if we hit play, we create a new game object and we invoke its main, just like we did previously at the bottom of all of those other examples. We had game main. That launches into the main loop of the game object until the player dies, because we don't actually have a player win yet. And then once that's finished, that'll return and we'll be back inside Kes menu's event loop. And they'll be able to select play again or quit. And that's basically how scenes are done. Okay. So, and once you're at this point of adding extra stuff, like menus and win-lose screens and things like that, you can also add extra juice. Add in extra image animations, particles. Every game is improved by the addition of particle effects. There's a handy Python library called Lepton. I actually had a bit of trouble getting it compiled on OS X Mavericks, because Apple users among us will know that Apple likes to break their compile chain for us every time they release a new version. Well, it's currently broken for Lepton. When you can get it working, it's really neat. It's got a lovely API, lots of flexibility for creating special effects in PyGame and OpenGL. But yes, particles, they improve every game. Lots of explosions, lots of trails, and all that sort of jazz. If you can get it working, the example platformer Cocos Juice, I think, is an implementation of the same game but in the Cocos library, which is, it's a kind of game development library layered on top of Piglet, but the same basic principles I've been talking about apply, and it has some particle effects that I just threw together in a few minutes added to that, if you can get it working. It works for me, but sorry, the name of the, I should probably, oops. Cocos Juice. Oh, the module name is 6. Oh, hang on. Sorry. Yeah, no, you need to be running Python 2. Oh, and you need to have 6 installed. Anyway, so this is Cocos Juice. Hang on. All right, so you can see I've got a little particle trail for the bullet there, and a little thing when you shoot the bad guy. Anyway, as I say, it seriously took me oh, I've got sound effects still. Excellent. So yeah, it took me a few minutes. I've also got the enemies rotating, because Cocos is built on top of Piglet, which is an OpenGL library, so things like image rotation is super cheap. And it also does a little scaling thing as well. Cocos, what it does is it provides a whole bunch of animation facilities. So the basic Cocos sprite, you just say .rotate, and it'll rotate forever. And you say .rotate, .expand, contract, or zoom in out, I think it is. And it'll just make it zoom in and out a little bit. So that's super cheap and easy to use. But yes, particles. Every game is improved with particles. All right. Okay, so inside that folder, you have, additionally, an implementation of Minesweeper, a very, very raw implementation of something that's like a top-down car driving thing. There's the side-scrolling shooter that I already mentioned. There's a tower defense implementation there. So if you're curious about how to implement pathfinding, it has a basic flood fill pathfinding algorithm implemented in it. Yeah, so Minesweeper, pretty simple. You're rendering a grid of cells. You're detecting the mouse clicks. So if you want to know how to do mouse clicks, it and the tower defense games are both mouse controlled. And on each click, you expose the contents. Very, very, very simple game. This is why Microsoft wrote it. Car driving game, slightly different movement model. You've got some trigonometry in there. It's not too scary, but it's there. There's some more complexity around the actual collision detection, so knowing when the player is on the track, knowing when they've run into a wall. Typically, you use bitmap collision detection for that, but you use a very pared down version. I'm not going to go through that now because I don't have time. The side scroller I've already talked about, though the side scrollers tend to be bullet hell, so you'll probably end up using one of the hash map collision detection mechanisms instead of the bounding box method that's actually used in the code that you've been given. Tower defense, handling mouse clicks to place towers, and then you have your creeps and their movement solution, which is just, as I said, it's a simple flood fill algorithm, and you can see that in the code there. Okay, so I'm going to talk briefly now about once you've got a game and you want other people to play it, how do you actually package it up for them to play it? So there's a few different. I don't know why Linux isn't on here, but it isn't. It should be. Okay, so we can generate a Windows executable, which is probably one of the easiest ways of getting people to play your game, because people know about Windows executables, they download them, they double-click them, away they go. OS X applications, slightly more complex, but the same tools that generate the Windows executables can generate OS X applications. And then there's deploying to Android as well, which is kind of neat. Okay, so the first tool that you'll run into in terms of generating Windows executables is Py2Exe. I'm just going to say don't bother, okay? It's old, undocumented mostly, or nearly all of the documentation is in a wiki page called General Tips and Tricks. And that's it. There's a lot of praying and dead chicken waving involved. This is an actual Py2Exe file for a game that I wrote called Match 3. Actually, I think this is part of the setup. It's nasty to figure out, and I'm just going to say just don't bother. Okay, so I'm going to skip through Py2Exe. There's a tool called Py2App, which is kind of inspired by Py2Exe, so a little bit nasty in its own way. I didn't get it to work, so it did not generate an actual OS X application for me. So then I moved on, and I found PyInstaller, which actually I didn't know about when I was initially writing these slides, but it turns out it's really useful. It does a really good job of generating applications for Windows and OS X. And I think it does Linux as well. It has two steps. You generate a spec file, and then you edit the spec file, and then you use that spec file to generate the actual executables and profit. Okay, so this is the generated spec file for my game. It does an automatic analysis of the code, the files that you've got. And if you ran this, you would get something, but it would probably be missing some of the data files because it doesn't really know how to deal with data files automatically. So you modify it to insert the things about the data files that you have. This is all documented quite nicely, so you're not in the dark here. And once you've added the data files, you run the bundler against the spec file, and you have your application, and it worked. So that's really nice. So PyInstaller, that's where to go. Don't use Py2Exe and Py2App, I don't know what's going on there. Android, you have a couple of choices. And I've done both of these. The PyGame subset for Android is pretty much most of PyGame. There's not much that's missing. So the game that we've developed today, everything's there for that. And it's seriously, and build, game, release, install will generate something you can actually put up like in the Android store for your game. There's a little bit of config that you need to write, and you'll see that in a second. Kivy, which is another toolkit entirely, isn't really geared towards writing games, but you can write games in it. But it does miss a lot of, it's more geared towards applications than games. So it doesn't have things like a concept of a sprite and things like that. But again, having said that, I have written a game in it, and it's on the Android store, and it's been installed like several thousand times, so there's that. Okay, so the PyGame subset for Android, you have to write a file, something like this. Oh, sorry, no, it generates this file after you answer some questions, and then you can modify it as need be, like updating the version number or what have you. And then the build process is quite painless using this spec file. Kivy, you write a spec file yourself, but again, it's not overly complicated. You're just specifying some information about the application. You do have to specify like the SDK version and stuff like that. I think you have to, yeah, I thought you had to do that for the subset as well. Underneath, I'm pretty sure these are both using the same basic interface of like Python to Java or Python to Dalvik or whatever it is under the hood, but then they've built their own things on top of that as well. But again, this is pretty painless. This just works and generates an Android bundle that you can install onto your phone or whatever. And yeah, and as I say, that's up on the store and has done pretty well for itself. It's free, download it. So yes, deployment. If you've got any questions about that, you can ask me, but it's actually pretty straightforward stuff. Of course, there's the generic Python caveat, which is you're giving away your source. But you know what? It's what it is. There's some things you can do to kind of obscure it, but in the end, the source is going out with the game, which can be okay. It hasn't done companies like Mojang any trouble giving away something that people can decompile and see the game code, because look at that ecosystem. So that's packaging. Content tools, I've already talked about SFXer. I've talked about tiled. What I'll do now is show you, in the few remaining minutes I've got, because I've got about 20 minutes to go, I'll show you a thing called Pixel Edit, which is pretty awesome, even if it is written in Adobe Air. I think it's the only thing that's written in Adobe Air, but it is pretty cool. But I will just leave you with, pygame.org has the docs. The website itself is a little bit out of date, they're working on that, but the docs are there and the docs are useful and you can download them. Invent with Python is an awesome book. You can get a free PDF download or you can buy a hard copy. And it talks about game development and it's a great introduction to programming to boot. And PyWeek, which is a challenge that I've been running for 9 years now, I think. Biannual, in 1 week, write a game from scratch. And it's a bunch of fun, and the next one is running at the start of May. So, that's the end of the slides. So I'm just going to now show you Pixel Edit, because it is, seriously, I'm not an artist, and I can create art in Pixel Edit. So if you've got any questions, jump in, but I do want to show you Pixel Edit. Oh, you turned it off again. It's all right. I don't really need it. All right. So the interface is typical kind of programmer interface. It's not the best, but it does get the job done. So the basic idea, well, the basic problem when you're generating pixel art is twofold. Most image editors don't give you direct access to pixels. They get fuzzy, and they're a pain if you're working at the pixel level. The second problem is that when you're generating tile maps, you want to be able to generate seamlessly tileable tile images easily. Nothing does that. some image processing tools like the GIMP or Photoshop will take an image and make it tileable by kind of fuzzing it and doing some nasty stuff to it. But what we want is to be able to just create art which is tileable, and that's what this thing does. So the basic usage of it is we'll create a 3x3 document which will let us generate a tile set. Okay, so we've got 3 tiles by 3 tiles here. And we can draw pixels on here, and that's fine. And there's our document over there. But where the fun starts is, let me see. Yes, so I've just hit tab, and this is displaying to me the tile IDs that are being used to render this image. At the moment, the tile IDs are blank, so I'm not using any tiles to render this image. The tile set is over here in this little box here. Currently, I'm not using any of the tiles. What I can do is I can select one of the tiles, tile 0, and say, all right, I'm going to use tile 0 in all of these boxes. Then, when I draw, it's replicated in all the other boxes. So, what I'll do is, let's see, zooming in a little bit there. All right, so I'm going to start off with some ground. All right, so ground is handy to have. Let's say, what's that? Dark brown. All right, so we'll fill that in with dark brown. I'm going to create a kind of a cobbly sort of ground. So we'll have some circles around here. If I go over the edge, you know, it's replicated around there, and it's already seamlessly tiled with, you know, itself, which means that if I draw this up in a game using this tile, it'll be seamless. This is the only tool that does this. Let's see, we fill these in. Blah, blah, blah. And I've learnt how to do pixel art not particularly well just by doing it in a bunch of different games. And you can too. Right, so now if I duplicate that, but then darken it down a little bit. All right, so we'll add some, oops, cancel button. All right, darken it down a little bit. Okay, select it. There is actually a facility in this for generating this button here, somehow, I'm not sure how yet because I'm still haven't figured that bit out, can generate the gradients you need for doing shaded pixel art. But yeah, as I say, I haven't figured that bit out yet. So I do my shading by hand. Anyway, so shading. We'll just whack some shading around the edges here. Whoops. We'll clean it up in a bit. Shading. And again, you know, I'm editing a single tile, but you know, I'm doing it in a way that it's, you know, seamless. This is kind of hard to do, looking across like this. In a seamless manner. And away we go. All right, I just want to quickly, no, I'm going to undo that one, that's terrible. I just want to finish off just this shading, and then I'll show you the next cool thing it does. Oh, it's terrible. I'm all over the place. I'm happy with doing like, you know, live coding, but apparently live drawing is not my thing. Okay, so that'll do for now. Okay, so that's one tile. So the next thing we need to do, so that gives us our base tile for our graphics. So this is the standard kind of tool set palette we've got. We've got the drawing and the eraser and the magic wand for selecting and stuff like that. The you know, eyedropper for picking colors. Then there's the tile placer tool, okay, which is a separate mode. And you can see the tooltip. There's a bunch of stuff we can do with this depending on which arcane combination of shift and click and control and right click that we do. What we want to do is control click to make a new tile from the canvas. So I want to say, because I'm going to create a new tile based on the existing tile we've got here, if I can control click, on the Mac it's command click. Command click, it creates a new tile in my tile set. I'll point to the screen, which is quite handy for you. And you can see that the tile ID changed from 0 to 1. So that's now the new tile. Okay, so I'll grab that tile and I'll put that all the way across the top there. And I'll get my green and I'll go, all right, so I'll have some green across the top. Fill that in. All right, and we have a nice bright line. You hold down Shift and draws a straight line. And I need a third, oh, is that, no, that's not the right color. I need a third color here, which is that, but darker. All right, and then I go, draw some shading here, a little bit of here. And away we go. We've got we've got tiles. It may or may not be lovely. We'll fill in that because that looks weird. Being beautifully, seamlessly tileable. Whether or not the art is beautiful or not is in the beholder, of course. But and then we need to start expanding out the repertoire so that we can do things like end tiles. So we control click again. Whoops, wrong tool. We select the tile tool. We control click, and then we can chop off the end of this to make this a right-hand end. And where's my scroll bar? Oh no, I don't have a scroll bar, do I? So then we control click this one. Command click this one to make another one, and that becomes the left-hand end. Or what we can do is, instead of doing that, we can say, all right, so what happened to that? Oh, I forgot to, what's the command for saying make a new tile from the canvas? So it is control click. Control click. So I can take this guy, and so I can paste that in anywhere. I can hit X to flip it, and there's my left-hand end. I just have to fix up the shading. And then I can hit Y to flip it the other way, and I've got, hang on. Oh, to pan around, you hold down the middle mouse button, and then you left-click. It's a bit, yeah. You could do the same underneath, but it doesn't quite look right, so you wouldn't do that. You'd chop out the bottom, and then you'd copy that over. But you can see you pretty quickly generating, and again, not an artist, generating some tiles for a game, and pretty straightforward. It's an amazing little tool. It also has tools for doing animations. So you're generating frames here. You can generate frames of animations, which I'm not going to go into because I haven't actually figured out how to do that yet. But the facility's there. And you can actually see the animation playing out, I think, in the preview box, and you can zoom along the animation and stuff. So it's really neat. It's not free, but it is donation aware. It's like you choose how much you want to pay for it, and I paid $10 or something. And I'll probably pay more because it's pretty cool. Anyway, so that's everything I have. We've got 10 minutes left if you've got questions. Anything really. Fire away, or poke around the code, whatever you want to do.
I have a question. You mentioned you had included some more demos in the file.
Yeah.
I don't think I've got them. Were they in the zip file only? Or?
Yeah, they're in the zip file. Yeah, there should be one called Minesweeper. There's the side scroller. There should be one called car driving. They're in the zip file? Driver, yeah. So if you didn't get, the USB stick has the files on it, so just grab the USB stick again. One of the three. Yeah. I think I can probably go off. Yeah, now. Thanks.